I'm really speaking not just for myself, but for Professor Ju, who's in the back of the audience here, and Professor Law, and Professor Sokolow, all of whom are part of the Thermal Sciences group in Mechanical and Aerospace Engineering. Let's see if I can. I want to emphasize the issue that we're most interested in is the idea of trying to reduce carbon emissions in net cycle over the next period of time. And you can see that we're talking about reductions here that are in the order of very large numbers in comparison to present CO emissions. In particular, the issue of transport and carbon emissions from transportation systems are thought to be one of the most difficult areas to deal with. And it's partly because of the size of the amount of energy that's being fluxed through the transportation system, as well as its source, which is principally petroleum. As such, we have to worry about backward compatibility for very large amounts of capital investment in terms of transportation systems, and also forward design issues. As we look at those issues, we can see that we want to keep some compatibility with the existing processing issues of petroleum. And what I want to emphasize is 2 points here. One is as we go from Saudi Arabian petroleum to the kinds of things we'll be using for petroleum in the future, the amount of energy processing requirement becomes very severe, principally because of hydrogen content in these fuels and the hydrogen upgrading necessary to shift the amount of hydrogen in the system towards what we want to use in real systems. This introduces a whole series of areas for producing hydrogen that are very important, but I think everyone now agrees that biomass is going to be a key to addressing these climate issues. The difficulty is that if we look at all of the renewable resources, including biomass, those numbers do not compare well with the total amount of energy production that we really require. For us as well, we have a very large amount of coal that's being used in electricity, and we know that China is going to increase its use in this area as well. So how do we deal with this? Well, there's at least 2 ways to process biomass. This is representative of one. I grow materials that have very high oil content. I extract the oil. I process the oil. And now you'll notice no oxygen in these systems. These are not the typical kinds of ethanol things that you and I are used to. They are now fully hydrocarbon compatible with petroleum products, as you see here on the left. I want to note one other thing here that's very important. These are the kinds of properties that are used to define what I put in a jet engine. If I go to a gasoline station and I collect gasoline today, tomorrow it's not the same. Next December, it's not the same at all. And if I do that in Asia or I do that here, it's very different. The question is how do I integrate these alternative fuels into those kind of problems? And this is why I need very strong compatibility. Now, why is this important? Because in comparison to kerosene derived from petroleum, this is the use CO2 emission that would have come from burning petroleum. But if I use any of these other oils, that use CO2 emission is replaced by the fact I photosynthetically captured the CO2 from the atmosphere. The problem is each one of these oils represents only about 40% of the mass of the biomaterial I grew, and the biomaterial that I'm using is very resource limited. So the amount of fuel replacement that I can get is very limited this way. Can I use it better another way? This is the other way. Not only can I use it better, but I can also develop ways of using coal. You've all seen the clean coal ads recently. It really is clean. The idea is to use photosynthetic sequestration of CO2 from the atmosphere to displace the CO2 that's going to be present in the fuel when it is burned. I'm going to combine it with coal. I'm going to generate a liquid fuel. I'm going to simultaneously generate electricity. So I'm replacing both the electrical generation market and the transportation fuel market simultaneously. The co-production of fuels and power turn out to achieve extremely good optimal economics with very good solutions of many of the environmental problems. Important here is that I can also eliminate very large amounts of the nanoparticle emissions that occur from pulverized coal firing by replacing it with gasification as the means of making my gasified streams. In order to do synthetic fuel conversion, I need to remove sulfur, so I end up with very low sulfur fuels this way. In addition, I'm going to process some of the synthetic gases to power right on site. And you'll notice I've got two routes to that, one this way, one that way, that I can also use liquid fuels with it. This is to balance the two processes. So oxygen firing of such a gasification system also produces a CO2 stream, which is very pure in its process, can be dried easily, can be compressed, and can be carbon sequestered and stored. That's the key to this technology. How big of an advantage is this? As I showed you here, we got about an 85% reduction in C emissions. If I do this purely with biomass in this problem, bio to liquids plus electricity, I get a minus 22% carbon reduction in comparison to petroleum. If I do this with 38% biomass with coal, I get a 0 net carbon cycle out of this process. I'd be happy to share more about the economics of this. This comes from an analysis with my colleagues, Bob Williams, Eric Larson, and the Princeton Environmental Institute here. So you can see that if I use one of these processes of CBTL, coal plus biomass to liquids with full recycle, carbon capture and storage, or once through, I can generate very good economic solutions to this problem. Turns out not the one that produces most liquid fuel is the best. This is. It's called systems analysis. I need to know a lot about heat rejection in these systems and its quality to pick that one. Okay, well, now what's the problem? This all looks very simple. The problem is this is what the molecular weight distribution looks like in any of the fuels we use for transportation. And we don't know how all of those little molecular weight distributions change every time I make an alternative fuel. I need to find ways of compatibility between alternative fuels and petroleum so I don't disrupt the distribution or storage or utility in any of these systems. So these are the questions that need to be answered, and these are the questions that the Thermal Sciences Group are addressing. We have a number of projects, and I'll try to keep everybody online here. We have a project called the Carbon Mitigation Initiative that's directed out of PEI, of which Steve Picala and Rob Sokolow are the PIs. It's funded by BP and Ford. We have a next-generation aircraft fuel project looking specifically at this problem for aircraft fuels and for producing very low net carbon emissions and particulates. That's PEI by me and involves the people you'll note here, all at Princeton. We have a Air Force MURI program, which involves a number of other institutions and PEI as well. And we are looking at how to model real fuels with what are called surrogate mixtures of small numbers of molecules. A similar program involves Professor Law. That's stationed on the West Coast, PI'd by Professor Egopopoulos at USC. You'll notice another set of industries, and you'll note who's funding this. Air Force is a big player in this area. And finally, we have hydrogen combustion in gas turbines. This is an issue with the syngas power generation problem and controlling emissions. We've been working with Nettle and also Siemens. And finally, just recently, we have gotten an Energy Frontiers Research Center award from Basic Energy Sciences, which Emily will tell you a little bit more about. So this gives you a kind of a broad picture of what thermal sciences is involved in here. We work on the fire safety aspects of this, on the fuel property aspects, and you'll notice the kinds of things you're talking about in terms of real-time sensing are very important for control of these kinds of systems. Thank you.